But then we also have our other inferential task, which is confidence intervals. And the sentence that I usually say sort of generically for confidence intervals is, what are some other reasonable values we could have observed? And the generic way that we come up with a confidence interval is we do our statistic plus or minus something that depends on the distribution and the alpha level times the standard error. And then again, in this case, because we're thinking about regression, our statistic is going to be beta 1 hat, or it's going to be, beta 2 hat, one of those beta hats, plus or minus the something that we're going to use is going to depend on the distribution. In this case, it's going to be a t distribution, so we'll have a critical t star value. But it's going to depend on the alpha level, what our t star value is, and it's also going to depend on the degrees of freedom, because the t distribution has degrees of freedom, times the standard error. Let's use that same example I was using before. So my beta 1 hat was 2.5, and plus or minus some t star times the standard error was 0.7. And so then the thing that is going to be challenging is finding that critical t star value. Again, if I was using the normal distribution and alpha equals 0.05, then my z star value would be 1.96. So we can kind of use that as a rule of thumb to see if our number makes sense. It's going to be around 1.96 because the t distribution is similar to the normal distribution, especially for big degrees of freedom, but it's not going to be exactly that. And so, again, you could use a t-table if you wanted to look up that critical t-score, but I'm going to use R. And again, we've got this thing where R is always thinking about things to the left. So here's my ugly version of a t-distribution. Let's say that I want an alpha level of 0.05. So I want 95% of the distribution in the middle and then 2.5% in either tail. And then what I'm looking for is, what's this number in the box here? It would be 1.96 if it was a normal distribution, but it's going to depend on the degrees of freedom for the t distribution. And so then I'm going to use the qt function. And then I need to tell R what kind of confidence level I want here. And what I'm putting into R is 0.975. And that's because R is going to tell us the line, the critical t value, such that this whole area is to the left of it. And so I can't just give it the 95 because R wants the whole thing to the left. So I have to give it the 95 plus the 2.5 to get the actual cutoff value that I want. So 95 plus 2.5 is 975, so 0.975. And then I can put in my degrees of freedom of 34. So then that would be my critical t-star value. It would be the 2.03. Again, it's not going to be exactly 1.96, but it's going to be in the ballpark. So I know I've used that function correctly. If I wanted to be really fancy, I could put into the qt a little vector made with the c function for combine, and I could say I want the line such that 2.5% is to the left, and the line such that 97.5% is to the left, and it would give me the negative 2.03 and the positive 2.03. Either way is really going to work. And then I could write out my interval. So let's see, 2.5 plus or minus 1.42, and that's going to be 1.08, 3.92. So that would be my inference for the slope. I'm 95% confident that for a 1 unit increase in my explanatory variable, my response would go up between 1.08 and 3.92 units. And that confidence interval agrees with my hypothesis test. So hypothesis tests and confidence intervals always agree with one another. In this case, that interval does not cross 0. So it is, I'm pretty sure that I have a positive slope because I don't see 0 in that interval. And we were able to reject the null hypothesis that the slope was 0. So that agrees with the conclusion from our hypothesis test. So that was just a little review of inference, specifically relating to regression coefficients.